Hello, wonderful people of the internet. Welcome back to another episode of Simuleo. So this is the second stream for today. As you can see from the fact that we still had drawings on the board. So right now, what I wanted to do is try another research stream. So I've got this kind of grandiose idea that we could do like open research in the future, right? And one kind of pivotal or one necessary part of doing open research, I'm sorry, I just hit everything. One pivotal part of doing this open research would be to be able to like live stream it and explain what we're doing and all that kind of stuff. So if you have questions, comments, concerns, things like that, I do really want you guys to bring those up during this stream. CT52, thanks for coming in. I also recognize that this stream is at a bit of an odd time for a lot of my normal viewers. So because of that reason, I don't really expect to have too many viewers here on this stream. It's mainly for rubber duck coding and debugging and that kind of stuff. So again, I'm going to do my best to answer every question, to kind of explain everything as in-depth and thoroughly as I can, with the hopes of having a better understanding of what it is that I'm actually doing with this simulation. But on the other hand, I also recognize that, you know, maybe we're going to go very in-depth into some stuff that, you know, might be very difficult for me to describe. So, you know, in these cases, I kind of need to be prompted as to when you guys have questions, you know, because if I'm not prompted, if you guys don't ask questions, then I'm just going to keep going and we might get very, very far before, you know, everyone's lost and no one has any idea what we're doing. So that's kind of the idea here. I just want to kind of go through, explain what we're doing, explain my research, explain, you know, why we're here, what I need to get done today, all this kind of stuff. So let's start by talking about what it is that we're actually going to be simulating here. So let me preface this discussion by saying it's the same discussion we had 2 days ago or whatever when we did the previous superfluid research stream. Basically, we need to calculate the energy of a superfluid system with a vortex in it. So that's the end goal. So we're just going to write down end goal, and this is to calculate energy of superfluid system. We'll say system with vortex. One second, vortex. Now here's the thing, as of last stream, I was kind of convinced that we already did this. Turns out we didn't. Turns out the energy calculation that I put in last time was complete garbage. I only took basic high school physics a year ago, so I don't think I have much hope of understanding this. Don't worry, I'm going to be going through things in a much more clear and understandable way this time. I'm not as pressured anymore to get this done because my boss technically left for a few days, so I feel like I have a little bit more time than I normally do. But I'm going to do my best to get this clear and understandable. Like, again, I would like to find a way to actually do my research live in front of everyone. But the truth is, when it comes to doing research live, I mean, there's just so much in-depth arcane knowledge you need in order to understand the type of research that I do. So it's not really clear how it is that I can provide all this information to everyone, especially, you know, random Twitch viewers, in a clear and understandable way, you know? So this is part of the thing that I need to figure out here. Okay, so let's go ahead and explain a few things. First thing, new page before, let's talk about what a superfluid is. Fluid. So a superfluid is a fluid that basically works without viscosity. So viscosity is a drag force in a fluid. If you move your hand around the air is a fluid. You can feel the air move through your hands, right? And that's viscosity in some ways because you can feel your hand being pulled back. Specifically in water or other types of fluid, you can feel the viscosity being like kind of the goopiness of the fluid. Now in a superfluid, you don't really have this. So as you move your hand around, you basically feel no drag whatsoever, which is kind of interesting. As a consequence of this, when you rotate a superfluid, and a consequence of a few other factors of what superfluids are, when you rotate a superfluid, instead of getting one large vortex in the fluid, you know, kind of like what you'd expect from here. So if I were to rotate this, second, you get a vortex in the system like that. Instead of getting one large vortex in the system, you end up getting a whole bunch of smaller vortices, which in this case pierce the condensate or the superfluid from the top to bottom. Now this is actually very interesting. Basically, vorticity in a superfluid, the amount of rotation in a superfluid, rather the number of vortices in the superfluid is quantized. You have 1, 2, 3, 4 vortices instead of a scale of a single vortex that is rotating faster or slower, right? So if you rotate faster, rather than getting, you know, making the vortex, you know, kind of thinner and have more power, you'll just get a new vortex. So like with 1 unit of angular momentum, you get 1 vortex. With 2 units of angular momentum, you get 2 vortices. So if this is our superfluid here, it ends up being that you create all these small tornadoes, which just kind of go from the top to bottom of your superfluid. So if we looked at it from another angle, these would be kind of going top down like this. Now, as an interesting note, these vortices must either end at the edge of the superfluid or reconnect in the form of 3D vortex rings and stuff like that. For our purposes, for this particular simulation, we don't care so much about the 3D nature of these vortices. If there's no viscosity, does that mean that these vortices would spin forever in theory? Yeah, in fact, as long as you have, sure. I mean, if you stop rotating them, then they will, they'll kind of do some weird things. But for the most part, yeah, I think they'll keep on going forever. I don't think there's anything inhibiting them or keeping them from spinning forever. So I think you're right. I think they do keep going on forever. I haven't really tried though. I guess we could try doing a simulation real quick where we spin up a couple vortices and we just let them go without any angular momentum. We could do that, but not right now. This would be something to try maybe over the weekend. So if you have ideas like that you want to try with superfluid simulations, let me know and we can totally try to do that like over the weekend or something like this. Okay, so what we care about here isn't necessarily the 3D nature of these superfluids. We care about the 2D nature of these superfluids. So we have a paper that's out on the archive right now where we have 4 vortices in our system. Okay, let me try drawing these so they're kind of level. So we have 4 vortices in our system. Let me try this again one more time. So we have 4 vortices in our system. Let me try drawing a circle. There we go. That's okay. If you, everything you do is, thanks man, I appreciate that. Okay, so we have 4 vortices in the system, right? The idea is that, if we're rotating with some angular momentum, we'll say at omega is equal to 0.3 or something like that. It's just some sort of arbitrary rotation frequency. These 4 vortices are in the ground state. They're in the lowest energy state. The idea is if we increase the rotation, sure, we could put another vortex into the system. If we decrease the rotation, we'll have a few less vortices in the system. But for now, as long as we're rotating with this speed, we'll have 4 vortices in this configuration. Now what we're going to do is we're going to keep rotating, but we're going to flip one of the vortices. So this means that instead of the rotation going around this way with each of the vortices, let's pretend they're all going around this way, this last vortex is going to be going around the other way. So that means we have 3 vortices all going the same direction and 1 going the opposite direction. This is going to be called an anti-vortex. And when we do this, basically the energy of our system goes from a very low energy state, again the ground state, as low energy as you can get, to an incredibly high energy state because now we've flipped a vortex, so it's going in the opposite direction. Now in the paper that we've presented here, let me just go ahead and get you guys that paper so you can take a look at it. Let's go here to, I'm just going to Google myself, James Sherloss, Google Scholar. And I'll get you guys the paper, just give me a second. I'm going to have to do G because DuckDuckGo does not bring up Google Scholar for some reason when I do this. Okay, let me get you guys this. And then when you take a look at it, so let's see, non-adiabatic Newton states, chaotic few body, this is what I'm looking for. Here. Let me just go ahead and open this guy up too. So yeah, we can paste it there, I believe. And let's open it up. So in this paper, we showed that the vortex trajectories become chaotic when we rotate, when we flip one of the vortices. This paper is in review. The reviewers were pretty happy with it, which is fair enough. So here then is the vortex trajectory, right? So we have the 3 vortices, vortex 0, 1, 2, 3, right? So that's our 4 vortices. If we don't flip anything, they kind of stay in spot, right? So this means that these are kind of plots as the vortices are moving with time. And basically you see based on this heat map, this one stays there, this one stays there, this one stays there, this one stays there. Once we flip one though, the trajectories become really chaotic. Well, not chaotic, but they start moving around like crazy. So here we have, them all moving around, and it's just because we're now in a high energy state and the condensate doesn't know what to do in the high energy state. Now, as a note, each of these vortices have a phase distribution. If you were here for the domain coloring visualizations we did the other day, you might remember, or you might have the idea of, kind of complex phases. So each vortex has like this kind of 2 pi phase winding. And that's how we define where the vortex is. Hey, Jerry, how are you? My first time saying hello to you twice in a day. Yeah, we'll see. I mean, again, these streams are not going to be particularly popular. They're kind of superfluid research streams, right? So, but I want to try to make researching kind of a bigger thing on Twitch, you know, because like no one does research on Twitch for obvious reasons. So I kind of want to make it, you know, see if there's a way to make this an interesting thing that people really want to watch, you know? And I don't know how to do that. So I'm trying a bunch of different things, you know, and we'll see how it goes. So anyway, each vortex has this 2π phase winding. And this is one way in which you can define where a vortex is by looking at its phase profile and trying to find these 2π phase winding locations. It doesn't matter so much, it's just that when we flip a vortex, we imprint a negative 2π phase winding in the opposite direction, which then flips the vortex and stuff like that. You're the Lewis and Clark of streaming theoretical physics research? I don't know if that's exactly true. I think other people have done some sort of research on stream before, but it's just been low-key. Okay, so basically we flip a vortex, and what we're plotting here is basically, okay, so here's what we're gonna do. We're gonna flip a vortex, right? And after flipping a vortex, we see that when we flip the vortex, we get these kind of weird trajectories. Now what we're gonna do is we're gonna check to see if we can influence or induce chaos in this vortex system. So what we're going to do is we're going to flip a vortex and shift it just a little bit, right? Just enough that, you know, for the first little bit, you're not even gonna notice that it's been shifted. Just shift it a little bit. And based on this small change in the initial condition, you know, flipping and shifting that the shifted anti-vortex by a bit, we do induce chaotic events. So what we're showing in this plot is that for the first 10 seconds, basically there is no change between the shifted and the non-shifted flipped vortex cases, right? So there is absolutely no change. But then after about 10 seconds, there is a huge change in the trajectories, right? And so now the trajectories are going all over the place, and this is how we can say, hey, we do have a chaotic system. That is to say, you know, at some point in our simulation, these two simulations that look almost identical do vary, and this is due to a very, very small change in the initial conditions, and that is basically chaos, right? So this is what we're trying to work with right here. This is the system we're working on, basically a small-scale simulation of chaos with vortex, with quantum vortices. Pime the Man, thank you so much for following. I realized I just missed that a few minutes ago. So this is the system we're working on. Now, as we got the reviews for this, someone asked a very interesting question. Page, actually we can keep this, right? So this is a high energy. Okay? Now the thing is, what happens if you only flip the rotation? What happens if you only flip the rotation? So by flipping the phase here, you are in fact flipping the rotation. That's what you're doing. So this phase is describing in some ways the underlying velocity distribution of the superfluid. So, you know, the vortex is spinning around this way. When you imprint a negative 2π phase, it makes it so it flips around this way. So that's what's happening when you change the rotation. That's kind of a way to interpret what this phase is doing. Okay. So, like I said before, this flipped energy case with the anti-vortex, and I'm just going to color the anti-vortex in red. But I mean, if you don't shift anything, it will only change the phase. Yeah, it does only change the phase. So let me see if I can re-describe this. So if you just flip something and you don't flip and shift, this is what happens. So by just flipping it, you get a very high, you know, you go from the vortices not moving at all to the vortices changing their trajectories a lot. So here, without flipping anything, the vortices are in the same location they always were. Then after flipping something, no shifting, just flipping, the vortices start going like crazy all over the place. Now this is in itself not chaos. The only way we can define it as chaos is if by some small change in the initial conditions, we see a change in the trajectories, right? So later we compare this trajectory here, this set of trajectories, to another set of trajectories after shifting it. So that's how we tell if it's chaotic or not. Okay, so let's keep going. So this is a very high energy state. The question is, how high energy is it? How high? That's the question. No, the truth is we don't really know. Bitbod Ben, thank you so much. Bipod Ben, maybe? Thank you so much for following, really appreciate it. Okay, so this is the question. How high is the energy? So we know that the energy of a simple harmonic oscillator, so let's do new page 4. Let's say we have a trap that looks like this, okay? And we put just some quantum particles in the system, right? And we simulate these with the basic Schrodinger equation, which is IH bar d psi over dt is going to be equal to, and I'm just going to put parentheses over here, and we're just going to say p squared over 2m plus v naught psi, something like this. Forgive my handwriting here. Psi, there we go. This v naught is a trapping potential right here. So this v naught is some sort of large harmonic oscillator like this. And if we just put quantum particles into the system, then basically we know that these quantum particles will create something Gaussian-like on the inside, something like this. And we know that the energy of this will be roughly equal to h bar, roughly equal to h bar in the 2D case. We know that this should be the case. In fact, it should be identical to h bar if our trapping potential is has a frequency of 1. It should be h bar omega over 2, just for the record. But in 2 dimensions, it will be exactly h bar if our omega is equal to 1 and all this kind of stuff. Okay, so we know what the energy is supposed to be. So this is going to be on the order of 10 to the minus 34, I believe, based on how you define h bar and stuff like that. So we know this is the energy of our quantum system in the ground state. Now, we're not in this state exactly, because here we're not working with the Schrodinger equation. We're working with another equation known as the Gross-Pedievsky equation, which has an additional term here, which is g psi squared psi. Okay? So with the Gross-Pedievsky equation, this term basically defines the interaction between a large number of particles. So if we have 10 to the 5 particles in our system, so it's 10,000 particles, they're all interacting with each other, right? And this interaction has to basically show itself in the Hamiltonian here, or in the Schrodinger equation. So because of that, this g psi squared term basically means that we can now have interaction between the particles. So instead of seeing this Gaussian thing, we actually see something that's a bit different. Here, let's see if I can draw it. It's going to look more like, basically more like a top hat. So it's going to go in here, and then it's going to very quickly go up, and then pop back down, something like this. It's the Thomas Fermi distribution or something like this. Now, in fact, we're not even here. We actually have a case where this is our system, but we also have these weird vortices in our system that, you know, go from, make our density drop down to 0 at certain points, right? So this is the system we're actually looking at, right? And so the energy should be around 10 to the 32 in this case. But the problem is, for some reason, all of my energy calculations are turning out really, 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 really crappy, and I can't figure out exactly why. So that's where we're at today. New page 4. This is what I need to kind of figure out, what I'm trying to do. Let me go ahead and get some water. And again, guys, just let me know if you have comments, questions, concerns, anything like that. Like, I realize this stream's not going to be particularly popular because we're doing like some sort of weird, you know, super fluid research. Ooh, I need to change my go live notification here. 1 second. So when you say harmonic oscillator, is that different from a simple harmonic oscillation, like a spring and Hooke's law? No, it's the same thing. It's actually called a simple harmonic oscillator because the potential, let me just go back a page. The potential here, V, is going to be equal to something, some sort of constant times x squared. So it's just some sort of x squared, just potential. Let me change here. Trying to do some research on stream. Let's see how it goes. Okay, go ahead and update information there. Okay, cool. So we'll see how this goes. I mean, again, as far as this stream in particular is concerned, I don't know. We'll see how it goes. I'm trying to see if it's worthwhile or if it's more efficient for me to stream this stuff or not. So, you know, it might not work out at all. But if you're interested in this type of material, just me kind of going through this, you know, more or less my daily work, just feel free to let me know. And if you're interested in seeing more of this, just say so in chat so I can see if this is something we want to continue. So now I'm going to go into the algorithm archive. You might ask, why are you going into the algorithm archive? Isn't this a side project that has nothing to do with your research? Ho ho, my friend. See, I'm an idiot when it comes to understanding quantum systems. So I wrote a section on quantum systems because I can never remember any of this type of stuff. So in this chapter on quantum systems, I specifically wrote down the energy calculation necessary to calculate, you know, the energy of the system in the ground state, right? So this is kind of what we have here. Let me just go ahead and grab this and put it down here. So the algorithm archive here has basically a general energy calculation. And let's describe how this works. Let me see, did I mention Brockett notation at all in here? I should have. should be the sum of the eigenstates. Yeah, I mentioned Brockett notation. But what I think I may have missed, it's okay, I think I may have missed this, but basically the energy of our quantum system, E, is going to be equal to psi times our Hamiltonian, psi. So let me go back a page and let me explain what we're talking about here. This guy right here, this side over here, p squared over 2m v naught g psi squared, this is our Hamiltonian. It's the thing that basically is moving our quantum system forward with time. So what we need to do to calculate the energy is this calculation here. Now what this means is basically we're going to be performing the integral from negative infinity to positive infinity of psi conjugate times h, so I guess we're doing h here, psi, with some sort of dx or something out here. Okay, so this means that we're going to be summing, basically operating on the wave function here, and then multiplying by the wave function conjugate. Now, if you have any knowledge of quantum systems before, you might recognize that this guy right here, psi star psi dx, is going to be some sort of probability density type of thing, right? So the idea is that the integral of psi star psi over all space should be equal to the number of particles you have in your system, so equal to n. Because the idea is that you have, n particles in your system, so you have a probability density that looks like this, for example. So you'd have 1, 2, 3 particles probably in your system. Then this should give you 3 at the end, because the idea is you're integrating your wave function across all space, and you're looking for basically however many particles there could be in your system. So what we're doing here is we're kind of introducing an additional h term here to this calculation, and that's really the only difference. So new page 4. Let's talk about how this works. I don't want to derail the stream with algorithm archive development stuff, but it seems like the title bar in sepia mode doesn't cut off the text correctly. Has someone made an issue? I think we have, but actually I think this is for all modes. Let me go ahead and change this to night mode, white mode. Yeah, so except for white mode. So it's actually only in white mode that this looks okay. And I usually use white mode, which is actually why I switched to sepia mode here for algorithm archive stuff. Because sepia mode, if there's going to be an error, we're going to find it in sepia mode, because that's the one no one uses, you know? All right, let me get some more water real quick. Okay, so now we're at this point where we need to calculate the energy of our quantum system. So let's just put down a simple Hamiltonian, and let's describe how we'd have to do this. Okay? And I'm really going slowly through this because I'm doing my best to understand how I'm getting to this point where I can't do a simple energy calculation. So this is also for my own benefit, along with your guys'. I mean, I'm hoping it's interesting to some people here, basically. Okay, so let's say our Hamiltonian is going to be equal to something simple. So we're going to say d by dx IH bar. This is going to be, wait a minute. One second. What is your momentum operator? I'm going to Google this real quick. I'm sorry. Just make sure I'm not doing something dumb here. Momentum operator. Momentum operator. Yeah, it's negative IH bar d by dx. Yeah, that's what I was expecting. So that means what we're looking for is it's going to be h bar, IH bar over 2m d by dx. That's going to be our momentum space term, plus some sort of potential, which we'll say is x squared. Sure. So that's our Hamiltonian. If we're going to be performing the operation psi star psi, right? So it's going to be psi star h psi. Then we need to operate this Hamiltonian onto this wave function. Okay. So to do this, what we're going to do is we're going to split this up into real terms. Here's our real term. I'm sorry. Here's our here. One second. Let me redo this. Here's our real term, which actually I'm going to do in blue. So here's our real term, and this is going to be a term in momentum space. So the idea is momentum space is kind of like some sort of velocity distribution, right? And so this Hamiltonian is based on some component in position space and some component in momentum space. If you read the Algorithm Archive article on this, you'll know that position and momentum space are conjugate variables. As the position space increases, the momentum space decreases. And the idea is that you can move back and forth between real and momentum space with a Fourier transform. So what we're going to do here is we're going to operate on our wave function. I just got out of extracurriculars. Hope I'm not too late. You missed a bit, but don't worry so much about it. So right now we're talking about how exactly we do the energy calculation, because we did something real dumb yesterday, and I'm not sure exactly what it is that we did. So I'm just hoping. I'm hoping we can figure it out today. If we can't, I'm just lost. I have no idea what to do. And again, guys, this particular stream is going to be really low in terms of population. I keep saying that, but I just want to harp that. Like, keep harping on that. Don't worry so much that we don't have too many people here. Like, kind of the point of this stream isn't the same as the point of the other streams. I guess this is kind of a general purpose test to see, again, if we can do research, like real research on stream. And if we can do real research on stream and there is like a lower population at these streams, does it necessarily mean that the other streams that I do will be less popular? I don't know. We'll try to figure that one out. Okay. So here we have h bar is equal to this, and we have h is equal to this. So this is our Hamiltonian of the system. And then the energy is going to be this computation here, just the integral of this over all space. Negative infinity to positive infinity. Whoa, hello. I think I saw 12 there for a second. It's okay, I'm not too worried about it. Again, this morning was pretty good in terms of viewership. And honestly, in terms of viewership, I don't really care that much about this. This is mainly for, just kind of being there in terms of transparency and stuff. LK Raider, Edge Cell 154. I don't know what that means, and I'm sorry. Okay, so we're gonna do this Hamiltonian here. So what we need to do is we need to deal with the real space and the momentum space components differently. So for the real space components, all we have to do is multiply x squared by our wave function, and then we multiply the wave function conjugate by that. Super straightforward, no problem. For the momentum space, things get a little bit complicated. So what we're going to have to do is we're going to have to do psi star, right? Because we have to multiply by the wave function, dot. Let's actually change these to dots so it's clear that these are multiplications and not conjugates. Now what we're going to have to do is the IFFT, bear with me here, IFFT of the momentum operator, which we're just going to call p squared over 2m this time, but it's the same thing as this guy over there, times the FFT of psi. Okay? So what we're doing here is we're moving this guy over here into momentum space, multiplying then by the momentum space variable, and then going back into position space so we can multiply by the conjugate, right? So we do a transformation to momentum space, multiply by the momentum variable, and then we go back. That's what we're doing. Oh, I'm sorry about that. Hey, LK Raider. This is my fault for like just having a crappy IRSSI terminal over here. So that's what we have to do. So we do, for real space, it's super straightforward. We just do this. For momentum space, we just do an FFT forward, multiply by the position variable, and then an IFFT back. If you are familiar with the split operator method, you'll know that this is actually the same thing we do for the split operator method. We take the guy in position space, we multiply by the position operators, we do an FFT forward, multiply by the momentum operators, and then go back to the position operator, and we just keep going back and forth like this. Now, let's describe the problem. These two guys are fine. Position space and momentum space, these guys are okay. I'm just gonna put a giant pink check mark on these guys. They're great, they're fantastic. Let me explain the big problem. I saw that and kind of assumed we're doing split op. What are we doing? We're doing an energy calculation here for split op. Tiny text. It worked. So we're doing the energy calculation. It's somewhat related to split op, but quite different, slightly different. Okay, so now what we're gonna do is we're gonna say, let's just go up here. Let's write down the Hamiltonian we actually have for our system. So our Hamiltonian is going to be p squared over 2m plus v naught, which is our potential, plus g psi squared. And then finally, we have an additional term, which is minus omega Lz. Okay? Now this minus omega Lz term, this is the thing that is giving us our rotation. Where Lz is our rotation operator. Works on Android as seen by my own eyes. Nice. So this is what gives us our rotation. Now there's two ways we can deal with this, right? On the one hand, we can absorb this rotation term into the momentum term. So our Hamiltonian actually looks like P minus ma squared over 2m plus v naught plus g psi squared. But honestly, it doesn't matter how we deal with it. The fact is we have to deal with this rotation term. By putting it in this way, basically we take this term and we absorb it in here and we just call it A, right? So we can do this if we want. Is omega the angular momentum or is that a squiggly W? Omega is the angular momentum, yeah. It is omega. Let me try. I'm just bad at drawing omegas. I'm sorry about that. So let's take a look at what this rotation term is and explain why it's a pain when calculating the energy. So this omega term is the LZ is going to be equal to x p y minus y p x. So this means that we have a variable that is in real space. So let's just do this. Real, momentum, momentum. So this means we have an operator that is half in real space or half in position space and half in momentum space. And this is why it's complicated. Because it means that if we're going to calculate the energy, we can't do this thing where we just FFT forward and FFT back, right? Now we have to perform a one-dimensional Fourier transform along, let's say, PY, to get them in a momentum space along PY, multiply by the appropriate operator, then IFFT back to get the energy of, like, for example, one term. And then to get the energy of the other term, we have to kind of do the same thing, right? Oops, sorry about that. So does that make sense? So here, we're running into this weird case where we're somewhere in between the two. How's my favorite scientist doing today? I'm doing okay, Canadian Sean. How are you, man? Let me get some water real quick. I've been drawing omegas very wrong. Look, I don't know how to draw omegas, man. I mean, I'm sorry, I need to do better. Okay, so now we have this LZ, which is equal to xpy minus ypx. And again, we can absorb that into the momentum term. We can do a whole bunch of different stuff. But for now, let's just deal with the fact that we have this operation in real and momentum space. Let's go here. Let's do new page 4. How's your archive going? My archive's going, the algorithm archive's going very well. I'm very happy with the amount of support people have given. We're going to be working on domain coloring again, I think later this weekend, and hopefully finishing up our new plot script for that so that we can finish up a plotting chapter, and then we can finally go back and do the revisions for like Fourier transforms and stuff like that. Now, one thing I'm doing during this stream is I'm constantly checking other notifications because this is technically my work time, so I need to make sure I'm not like missing meetings or anything. I checked beforehand and I don't think I have any meetings today. But also there are other people working on this problem. I gave them all the information I had, and genuinely we're trying to figure out what the problem is and why our energy is so wrong. So let's talk about the split op method first. Let's just Control Z here. So first, split op. Like I said before, the split operator method is the thing that allows us to apply the Hamiltonian to our quantum wave function and move it forward with time. Every time step, we move to momentum space, multiplied by the momentum space operators. We move to position space, multiplied by the position space operators. Fine, fair enough. And by implementing this method, by applying the Hamiltonian this way, basically every time step we move forward with time. The Hamiltonian is the thing that allows us to move forward with time. Now, if we have this term that's somewhere in between real and momentum space, what we do in the split up method is something a bit weird. So we're going to do an FFT. We're going to do an FFT, but it's only going to be a 1D. So we're going to say 1D FFT. Ooh, this is going to be complicated. 1D FFT. I'm actually going to move this over here. So we do a 1D FFT of our quantum wave function, psi. We multiply that by our, So FFT, and we're going to say it's in the x direction of our wave function. Then we multiply this by our ypx term. So that's a negative, right? So that's going to be multiplied by that. And then we do an IFFT, so IFFTX to go back, right? So now we have a specific FFT in one dimension and a specific FFT in another dimension, right? So we have two FFTs, one in the x dimension and one in the y dimension. And then additionally, if we're in 3D, we'll have one in the z direction too. Will we be implementing domain coloring in other languages or just have new plot and Julia scripts? In principle, sure. You can implement it in whatever language you want. But for the start, we'll just have new plot in Julia. I don't see any reason for complicating it further than that. I like the fact that new plot is kind of this standalone plotting program, so it's kind of nice to have. Okay, so this is how we'd perform the operation in, this is how we'd perform the XPY operation. And then what we do to perform the YPX operation is we do an additional thing on top of this. So now we're going to do the FFT of y times x to y, times this, and then we do the IFFT of that. Okay, So the idea then is that we have this guy that we have to move, again, half. So we move half in momentum space. So half, and then we move again, half again. Does that make sense? So we do an FFT forward in the x dimension, multiplied by the x component, FFT backwards in the x dimension. FFT forward in the y dimension, multiplied by the y components, FFT backwards in the y dimension. So we go, one dimension, other dimension. That's what we're doing. This is how we implement it in the split out method. Now, like I said a second ago, for the most part, for the energy calculation, we're doing the same operation for the energy calculation. We're Fourier transforming forward, Fourier transforming back. So it would make sense that we basically perform the same operation for the energy calculation. It's just for some reason. So the subscripts, there's subscript X and Y. I'm just bad at drawing subscripts. I'm sorry about that, Ben. Much better is to put camera into paper with pen. Much better is to put camera into paper with pen. I don't know. I'm happy with this setup, actually. Hey, Husky, how are you? I think this is fine. Besides, it's actually even much harder for me to set up such that I can just do paper and pen. I was thinking about, like, if I could, I'd have like a blackboard behind me and we just do everything on the blackboard, but I just can't do that, not with the current setup. Also, I can't find a way to do paper and pen with this setup too. Started learning PyTorch? Oh yeah, you definitely have. Okay, so you'd expect that the energy calculation is something like this. But for some reason, and this is the thing that's really weird, page new, page 4. Like I said, we're starting this simulation, or we have the idea with this particular project that we want to find the energy of a system with 1, 2, 3 vortices, where 1 is an anti-vortex, right? But for some reason, the energy of the system, no matter what I try, gives us an energy of 10 to the minus 32 for the, we'll say potential. So we'll say position space and momentum space components, which is about right. But then it gives us something on the order of 10 to the minus 13 or something like that for the angular momentum operator, or for the angular momentum energy, which basically means our angular momentum energy is like 10 to the 19 times bigger than any other energy in the system. And that is so freaking weird. It shouldn't be that different. It should be basically on the order of the trap depth. And the trap depth here is going to be basically on the order of 1. So we really shouldn't be seeing anything more than maybe 10 times increase in energy. So it should be, unless I'm completely wrong here, on the order of 10 to the minus 31 or something like this. This is what we're looking for. Something on times 10 to the order of minus 31, but we're getting something times 10 to the order of minus 13. And before you say it, no, I'm not just being dyslexic. So what I'm trying to do today is just mess around with things, try to figure out how to get this energy calculation working, because I'm convinced that this is correct. Like doing some sort of energy calculation by doing a transformation like this should be right. But for some reason, it's not working out. I don't know why. I love that deep learning course at my university switched to PyTorch. It's like I know that you're trying to say, but I see XPY and I instantly think permutations. Oh yeah, fair enough. Sorry about that. I mean, the course is easy as heck for me right now, but it's fun. Learning, literally me in first year computer science course right now, learning Fortran and C, I'm going into final with 99%. Yeah, to be fair, that's pretty, I mean, you've got a pretty good understanding of basic computer science, so I don't think you'll have any problems with that. My local college let me jump into algorithms, which is pretty nice. Oh, nice. I have a pretty cool idea for a course project, but I don't know if the proposal will pass since it's not a lot of code. Okay, so what I'm going to do next is I'm going to actually start jumping into the code here. I walked through everything, which is good, but I can't seem to figure out what the problem is here. So I'm gonna walk into the code, we're gonna try a bunch of things. If you guys have questions, comments, concerns, ideas for how to attack this problem, just let me know. Because, you know, as we go into it, it's just gonna get complicated. I don't understand how to solve this problem. Got a 4 out of 5 for my algorithms course. Had to redo the exam and just got the exam passed. You know the big boom in pre-trained language models for generating text. Okay, so I'm gonna pop over here. We're gonna cd into projects at GPUE, and I'm gonna do the same thing for this terminal. cd into projects GPUE. Now I have a specific. Oh, hello. Come on. I have a specific branch, so git pull origin energy fix, and we're gonna just mess around with some code. So I'm gonna also open up Julia over here in this terminal just for some quick tests. Julia. Okay. So I'm gonna go over here. I'm gonna say using plots, and I'm just gonna show some FFT stuff over here just to make sure things work as anticipated. So now let's go into VI. I think I called it Julia energy calc.js. So here's our energy calculation file right now. What do we have here? They aren't giving out their source code. Let's see, I had this idea where I could use images to generate stories. They gave out the main model, but not the distributing training code. Don't people use GANs a lot to do the opposite, where you generate picture based on text? GANs and text notorious hard, as far as I know. Yeah, I don't know anything about this. I'm sorry about that. Okay. So here we have a function to calculate the energy. We're going to be reading in the momentum space Hamiltonian operators, the real space Hamiltonian operators, our AX and AY, which are XPY and YPX in this case, our G, which is going to be just for the G term in our gross PDSC equation. So let's see if I can go back. It's this term right here. It's the interaction term between all of our quantum particles. And then, one second. We're also going to be reading in X dimension, Y dimension, dx, and dy. Okay, the first thing we do is we create wave function k, which is going to be our wave function in momentum space, and wave function conjugate, which is just going to be the conjugate of the wave function. Then we do the energy k calculation here, which is just going to be equal to the IFFT of hk times wave function k. Again, we transform forward, multiply by the 31 and 13 just reverse string. Yeah, I made a note there. I'm not being dyslexic. I'll explain. I'll show what's happening here in just a second. So we have wave function c. So here we have wave function c dot times IFFT of hk dot times wave function k. So again, we Fourier transform forward here, and then we IFFT this multiplication back before multiplying by the conjugate. For real space, we do something quite similar to what I said before. We just add in this real space term. So it's going to be the absolute value squared of the wave function times g times 0.5. That again comes from this gross PDSC equation, where we have a g squared over g times psi squared or whatever. We multiply this by the wave function, and then we do the wave function conjugate. Here we don't require any Fourier transforms because we're always in real space, which means we don't need any Fourier transforms. Finally, we have the energy L, which is the angular momentum energy, and this is the thing that's kind of kooky, and I can't quite figure it out. So one of my friends says that this should be the energy for energy L, where we do a sum of the energy from the X component and a sum from the energy from the Y component. However, in that case, I don't understand why he's got these negatives here. So then I tried, well, let's just try adding them together. And that gives us something really weird, and it's not quite right either. So then I thought, well, why don't we do this here, where we just do literally the step that we do for the angular momentum, where we do a 1D Fourier transform forward. We do this step over here. Let me see, where is it? Where is it, actually? This step here. So this is a step I added in for this third guy in here. So it's FFT forward wave function along one axis times AY, again along that axis. Then we do an FFT forward of this guy along the second axis, multiplied by the second axis, then multiplied here. I don't know what the deal is. There's going to be a problem here. I don't know what the deal is there. And then in the end, I just sum them all together for an integral. I know Julia has a sum function. I was so not trusting basically anything that I was doing. So I was just like, look, let me just write out the sum explicitly, just because I thought something else would be wrong. Technically, my idea could be done with a linear transformation, but I'm guessing a layer or two would be better. Since my idea includes using pre-trained models, part I could be done as a linear transformation. Again, I don't know so much about this. Okay, so I'm gonna go ahead and just plot some stuff with Julia over here on the side. We're just gonna mess around with some stuff. So I'm gonna say, I'm gonna create a variable called A, and it's gonna be equal to, what'd you say? It's sine of 2 pi divided by 100, and then times I. And then we'll say for I equals 0 to 100. Okay. Now I'm going to go ahead and plot A, just to make sure we have the sine wave. What's the input for this program coming from? The input's coming directly from GPUE. So what we have here is GPUE is outputting the XPY term, the YPX term, the momentum space operator, which is just p squared over 2m, the potential, and then just various wave functions. So we have various input wave functions from the real and imaginary space. So we have, here's the imaginary space component, here's the real space component of some wave function. So here's a loaded wave function, here's after some steps in evolution, 0 steps in evolution. Great, okay, so we have sine. So let's go ahead and do the FFT of this. So we're going to plot FFT of A, and I believe I'm going to have to do the absolute value of that. I think it's going to have to be dot here. FFT, oh, you need to use using FFTW. Okay, now we're going to try that. Give that a second to run. Okay, here. And this is exactly what we'd expect from the Fourier transform of a sine wave, right? We have one peak at 1. Fair enough, that's what we expect. Let me go ahead and modify A a bit. So we're going to say A is going to be equal to 2 pi, but we're going to increase the frequency to 4 pi. Oh, let's do 12 pi. Let's get crazy here. 12 pi. And then we're going to run the Fourier transform of that, and you'll see that we have the peak slightly shifted forward. It's fine. This is what we expect. Okay, so now what I'm going to do is I'm going to create a kind of 2D heat map here. So we're going to say 4. Let's just say B is going to be equal to zeros of, we'll do 100 by 100. Okay. Now we're going to say 4. I equals 1 to 100. We're going to say B of whatever row we're on, I, is going to be equal to A, and mismatch 101 aligned array. Wait, how big is A? A is a 101 element. How is A 101 elements? Oh, okay. That's my problem. So now let's try that again. Okay, nice. So now we're just going to run a heat map of, there we go, of B. And we should just see, yep, okay. This is what we'd expect. So what we just did here was we did a heat map of B. So here we see a wave that's kind of going up and down, up and down, up and down, up and down. So that means we have a wave going in this dimension. If we perform a Fourier transform along the y dimension, we would expect to see kind of that same thing we saw along 1D where we see a peak and then another peak. We're going to expect to see the same thing if we perform a 1D Fourier transform along this way, right? But if we do a 1D Fourier transform along this way, we're going to get something weird that doesn't make any sense. Let me go ahead and catch up. Nice, let's see. Answer set programming, I'm not sure what ASP logic is. Actually, kind of like logic programming. I don't know much about this again, I'm sorry about that. Okay, so what I'm going to do next is I'm going to do a heat map of the FFT of B, and I'm going to do the absolute value of this. Okay, so here's what you see. For just a standard FFT, it does kind of a dot here and a dot here. That's not, this is just an FFT, not 1D. So now if we do an FFT 1D along one dimension, this is just along one axis, axis 1, whatever that means. It means that we see these two lines. So again, this means we had a wave that was going like this. We performed an FFT, and now we see the two peaks kind of coming here and here, which means we're in frequency space on the y dimension, right? So this means axis 1 has to be the y dimension. And just to be clear, let's go ahead and create another B. Except we're going to call it C. And we're going to do the same for loop we did before, except we're going to define this as C. And here's I. Here's that. And now we're going to go ahead and heat map C. And this, you should see waves going this way. And so now if we perform, here we see the waves going that way. So now if we perform an FFT along this dimension, we should see again those two peaks, one line here and one line here. So what we know is axis 1 is along the y-axis, and axis 2 should be along the x-axis. So if we perform this, it should be C2. We should see, yep, just two lines, just like that. Nice. So this means that if we perform a 1D FFT, by doing axis 1, we're going to get the y components. And if we do a 1D FFT using axis 2, we're going to get the x components. Great, fantastic. So then in that case, this method of calculating the energy here should be fine, because we're doing axis 1 and multiplying by the AY components. And then we're going to do axis 2 multiplying by the A2 components, because AX is along axis 2 and AY is along axis 1. Okay? So that should work just fine. So Control D. I'm going to spin us up a quantum wave function with a few vortices present, and we're just going to run this energy calculation, and we're going to see what happens. Because I see no reason why this energy calculation shouldn't work. It seems fine. So if this calculation does work, and I'm just being an idiot, then the truth is that there's something wrong with the input data that we have for our 4-vortex system with the flipped vortex case. And that's something that we have to kind of look into later. I love how I got scores close to 100 by 100 from search, probabilistic stuff, reinforcement learning, etc., and then 47 out of 100 from ASP. What was InstaSet's program? Yeah, I don't know so much about this at all. I'm sorry. I need to learn more. There's a lot I have to learn. I know this. Okay, so let's just go ahead and run history, grep GPUE, because I think I should still have some commands in here. Looks like we have a couple 256 GPUE simulations here. Are any of these what we want? 50,000 plot 5,000. What's the data directory? I think it's okay. So let's cd into pi. Let's just run the last history grep plot. Let's see what we have here. So I should be able to run number 453. Okay, so here we have our initial guess wave function. This is just a standard Gaussian. And as we move forward with imaginary time, we're trying to get closer and closer to the ground state of our system. How would we know if the NRG calculation is correct? What is NRG? Yeah, I don't know. What does NRG stand for? Okay, so here we start there. Oh, energy. How do we know if the energy calculation is correct? One way we know is by testing it against a simple harmonic oscillator case. Since we know the... yeah, I'm sorry, I misunderstood. So because we know the energy of the simple harmonic oscillator in 1 and 2 and 3D, we can check the energy calculation based on this. Outside of that, I don't really know how we know what the energy is for a single vortex case. We have to rely on physical intuition, which I hate relying on, but it seems like something we need to do. Okay, so we should see vortices appear in the system about now. And so now we see a whole bunch of vortices in the system, right? Cool. Okay, so that last plot that we saw there, we just saw a whole bunch of vortices in the system, which means we do have data to work with here. So what I'm going to do is I'm going to, this is going to be a dumb way to do it, but I'm just going to do it this way. I'm going to read in that data, where all this stuff is going to be now in the data directory. So we're going to say data directory is going to be equal to, and we're just going to say it's equal to /data, because I think that's correct here. And now we're just going to put that in front of all these guys. So it's going to be data directory concatenated with this guy. We're just going to add this in for all these guys. There, there, there. Just adding this in here. There, and there, and there. And let's go ahead and modify these guys based on the parameters that we ran for this simulation. So let's go ahead and open these up. So it's going to be, again, this is a very simple script. I didn't really mess with this script too much. I could have done a lot of things like read in the parameter script itself. I didn't do that. This is literally just implement these details for yourself. Just like read the parameter script and go with that. So I'm going to go into vi.self/data, and it should be under params.dat, and I'm looking for x dimension, which should be x dimension, which should be 256. Yep. And y dimension is the same, 256. And we're going to do the same thing here, 256. And I'm looking for dx over here, dx. It's going to be 1.72 times 10 to the negative 6. Y dimension should be the same. Oh, hello there. Let's try that again. Nice. And so here we're just going to do $, and we're just going to paste that. Oh, there. And we're going to paste it again down here. So $, paste. Okay. C252, thanks for coming in. What's up with the dot multiply operation? So that is a pointwise multiplication. In Julia, there's a difference between A times B with just a single star. This will do a standard matrix multiplication. So we'll do like this times that, right? It'll do the flip. But if you do dot times, it just will do item by item. So it's a pointwise multiplication. And the last thing I need is the G. So let's see, it's going to be G, I believe. Oh, hello there. Let's try this again. G dense, which is 6.8027 times 10 to the negative 41. Why is this times 10 to the negative 41 in this case? Okay, I don't really care that much. Okay, so let's check to make sure dx and dy are the same. dy is 1.72, and let's check to make sure y dimension is also the same. Y again. It is 256. So I think this is all the variables we need. So now let's just run Julia. Calculate energy. Julia, calculate energy. Give this guy a second to run. Error, load error. Gonna open data wave function EV. That's my bad for misnaming it. Let's open it up again. Again, guys, please keep coming up with questions and stuff. I'm literally at my wit's end here for figuring out this energy calculation, and I have no idea what to do. So we're just gonna go into Julia, calc energy, and let's just go down to the data directory because I needed to put an extra guy there, and this should be fine. Let's try that. Error, load error. What on earth? Data wave function EV0. Why are we even trying to open that one up? Oh no, we are definitely trying to open that one up. Let me look at the last GPUE command. History, grep GPUE. It looks like no, we should have an E0. Let's try plotting it real quick. So Python plot.py I, it's gonna be wave function EV. Why not? G256256, and that should be correct. Yeah, this is the state we want. Well, then what's your deal, dog? Is the energy expression different from the algorithm archive one? No, it's the same as the algorithm archive one. It's just that in addition to the I guess Hamiltonian we had there, we have two additional terms, one for angular momentum and one for the g psi squared term to make it a superfluid, right? We can deal with the g psi squared term without any problems. The problem is the angular momentum energy, the rotation energy here. So because we're dealing with a vortex system, we have to deal with some additional components, and that's why it's complicated. Okay, that looks correct to me. So, oh, I see the problem. It should be, no, I don't see the problem. Where? Wave function EV0. Data directory, it says it doesn't exist. Aha, I know why. I was in the wrong directory. Fair enough. Okay, give that guy a second to run. It says energy of 5.46 times 10 to the negative 9. Okay. That's fine for an energy, I guess. Okay, so the issue here is that, I'm sure that's fine for an energy, but here's the issue. Let's go to vi calc energy.jl. And what I'm going to do is I'm going to comment this out. So basically, we're only going to be putting in the real and the kinetic parts here. There. Okay, so by just putting in the real and kinetic parts, we now have something that is an energy 1.039 times 10 to the negative 32, which means that the rotational energy here is times 10 to the, it's just impossibly larger than the energy of anything else. And that's the issue that I have with this. It shouldn't be that large. We shouldn't have that high of an energy in a quantum system. Because this is in joules. Like, this is actual, like, units of energy. Okay, so cool. We're kind of messing around with this. We're going to see what we can do. I'm kind of convinced that... Okay, so what I want to do then is I want to check the energy as, you know, kind of a function of time. So let's go to calc energy here. And what I'm going to do is I'm going to create a new function here, which is just going to allow us to kind of check the energies for a range of different values. So we're going to say, I guess we already have calculate energy, so maybe we need to say calculate range, I don't know. Okay, and we just give it a range, so it's going to be uptime. Oh, nice, we have an uptime. But I don't think that's correct, because I have not been up for 3 hours and 6 minutes. I've been up for 1 hour and 6 minutes, but I was also up earlier today. Okay, so what we're going to do is we're going to read in three values here. It's going to be the value of start, which is going to be an int 64. It doesn't have to be 64, I don't really care. End, which is going to be, again, an int 64. And then we're going to have increment, which is going to be an int 64. Okay, we're going to end it down here. And then we're just going to grab all of this stuff. And this int 60, thanks, Ben. Let's change this to 4. I'm just going to take all this stuff up here, and I'm just going to paste it down there. So 1, 2, 3, 4. D22D, paste down there. Okay, I'm just gonna add some spaces. Okay, so this means every time step we're gonna have to read in certain values, read in and reshape certain values, and those values will be the wave function. Let's go ahead and do dd here, dd there, and paste that down here. And also I forgot to space these guys. And then the other guy we're gonna have to do is reshape here, so dd and paste that here. Okay, the data directory should be the same. All these guys should be the same. So now we're just gonna say for I equals 1 to, I guess it's going to be start to end in increments. Now here's the thing, I don't really remember what's going on here. So let's go ahead and do here, end there. Okay, there's definitely something up with energy L, but I'm not sure what. What are you multiplying everything? Wasn't there a sum in there somewhere? Where was the sum? So there's certainly something wrong with energy L, but I'm not sure what. Why are you multiplying everything? Wasn't there a sum in there somewhere? There was in fact a sum in there somewhere, definitely. But the sum was for this. So here, let's just write this out. So the omega LZ term, LZ, is going to be equal to omega times x p underscore y minus ypx, right? So the sum here, the first one is the only one that looks remotely correct. What do you mean the first one's the only one that looks remotely correct? Wait, what's the first one? So the sum here is, let me think. So this is going to be operated on psi, right? And there's a minus sign in front of this guy to begin with. Yeah, okay, you're right. Yeah, the first one might be correct there. The truth is, I tried the first one, and the first one also doesn't work. So let me show you what happens when we do the first one. Instead of that one. Encode the expectation value over LZ. Yeah, I know what you mean now. So let's grab this, and let's do the first one here. Oh, Tim, thank you so much for the raid. I hope you had a wonderful stream. I realized I rated you and then you rated me back, so, you know, I'm sorry about that. But I hope you had a wonderful rest of the stream. I popped into the start, or yeah, around the start, and then I kind of left after a bit. And then I started streaming again because now I'm actually streaming work. So yeah, feel free to talk about your stream. If you guys in chat don't know who Tim is, he's a wonderful programming streamer. He does a lot of game dev. I definitely recommend checking him out. I usually check him out just before bed every night my time. So definitely check him out if you can. Okay, so what I'm gonna do is I'm gonna calculate the range here. And let me just go here into Julia real quick. I'm just gonna open up Julia. And let me just do a quick for loop because I'm actually not sure the notation for for loops here. So we're gonna say for I equals 1 to 10 in steps of 2. Print line I. End. I misspelled print. 1. Okay, so this goes from 1 to 2. So we want 1, 2, 10. Yeah, that's what I want. Okay, so let's go here and let's go ahead and change this. So it's increment. And then it's end over here. And then down here it'll be start, increment, end. And so we do calculate energy, and what we're gonna have to do is we're gonna have to modify this. So we're gonna do EV. Actually, this is gonna be wave function 0, const. Yep, that should be right. And then we're gonna concatenate this with string of I. And then down here we're gonna do the same thing. So it's gonna be wave function data directory, except instead of EVI, it's gonna be 0 const I for the imaginary component. Sorry, the notation here is a bit funny. I apologize for that. Times string I. Okay, times the imaginary. I'm just gonna pop this down to the next line, just so that we have some spacing in here. Oh, hello. Okay, thanks for the shout out. I do have to run to bed though. Night, everyone. So yeah, thanks so much for coming in. Thanks for the raid. Have a wonderful evening. And again, if you're here for the first time, so what we're doing right now is we are basically doing, well, we're doing my work. So what I'm doing is a quantum superfluid simulation, and we're trying to check the energies of the quantum system in the end. So that's what we're doing, and we're trying to make it work. I can't get it to work at all, and so it's kind of driving me nuts. Okay, so let's go ahead and calculate the range here. So we're just going to go down here, x, and we should be able to calculate the range that we just did. So it should be calculate range. I realize this is a dumb function. I'm not too worried about right now. So let's see what we have over here. Sorry, Control D. ls data. So it should be, I think it's going to be 1 to 50,000. So it's going to be 0 to 50,000, I believe, in steps of 5,000. Okay, so that should work. See what happens if we run Julia. Come on, Julia calc energy.jl. Load error, syntax error, unexpected end. Okay. Oh, I see. That's because we'll call it final. And again, guys, if you have any questions, comments, concerns, feel free to ask, and I'll totally address them as soon as I see them in chat. Start not defined. What do you mean start's not defined? I'm reading it in. What? Start not defined in online. Oh, we start another. No? Okay, I have no idea then. I feel like it would be energy L equals negative wave function. Second hander, thank you so much for following. Really appreciate it. I feel like. Oh, I see. Yeah, we can try this. Let me just let me get this working, and then we'll try some different guys. I'm using Metasploit currently on Linux Mint. I'm not trying to crack my phone. Oh, fair enough. Yeah, nice. But no, apparently what? Okay, so we're going to calculate energy here. Okay, so what's the issue? It says, especially starting at start not defined, undefined value error. But I think, what am I doing wrong here? Range is start in 64. I equals start increment final. What on earth? Let's see. Undefined value error. Where is this at? It's going to be at 27. Wait, what? Ah. Calculate range not defined. Calculate range. Calculate. Oh my gosh, one day. Try it again. Julia, let's go. Did I put it in the wrong order? Shoot. Start increment. Yes, you're right. I did put it in the wrong order. Because Julia. Let's go. Julia, calculate energy. Let's take a look at these energies. Yes, what's up? How are you, second hander? Handler failed to bind 1.92. Okay. Calculate energy.jl. Now let's go ahead and add in the energy L component. Give it a second. And yes, that is incorrect. That is certainly incorrect. Okay, let's go into VI calcenergy.jl. Okay, so we have this guy. It is so sad. I'm sorry, I can't help you, but permission denied, man. Okay, so let's see, wave function conjugate. So let's see, Ben said I feel like it should be negative wave function conjugate times IFFT of AY, FFT of wave function 2, minus IFFT of AX. Yeah, this is what we have here. Oh, you did an IFFT of wave function 1. Why do you want an IFFT? Oh, I think you meant FFT there. Yeah. So that's this first guy. So here's some problems, right? So first of all, there's multiple problems with this. The first problem is that without calculating any of the angular momentum, all of these are times 10 to the negative 33. With calculating the energy, all of these guys are flipping between positive and negative, and they're, for some reason, just way, way too high. I'm not exactly sure why. The first minus shouldn't be there. Calculate energy.jl. So wave function conjugate dot times negative IFFT of AY minus. So here's the thing. I'm pretty sure this has to be a plus. If anything, this has to be a plus. And the reason it has to be a plus is because this xpy minus ypx, this minus ypx is absorbed into the ay term. So ay is equal to, I'm sorry, ax is going to be equal to negative y. So we already have the y, the negative y in the in this component, right? So it should be okay. So let's try running this with the positive, but with the negative out front. So let's do Julia Calc Energy and give it a second, see what we get. Yeah, but then we get all these random negatives up front, right? So having a negative energy doesn't make any sense in this case. And that's what I can't figure out. Why are we getting a negative energy at all? More than that, look how the energy is consistently increasing. It should be that as we're moving forward with imaginary time, the angular momentum or the energy at all should be decreasing, right? Because the idea of imaginary time evolution is that our solution goes from some sinusoidal oscillation to an exponential decay in the energy. So we see the energy exponentially decaying off. And so we should be seeing the energy start really high and then drop way, way down. But that's not it. Should the part of the energy process be squared? I don't think so. Because, you know, okay, let's see here. Page before. And maybe it should. But the fact remains that we are actually getting the correct energy without squaring it. See, I was adding them in quadrature because I thought maybe they needed to be squared. But the thing is, we're getting the right energy without squaring it. I mean, maybe it needs to be absolute value squared, but even so, the thing is, even if it is squared, these energies are still way too high, right? Because we should be getting something on the order of 10 to the negative 32nd, but we're getting something on the order of 10 to the minus 7. So we are 25 orders of magnitude too high, 26 orders of magnitude too high. And that's the part. That's the part I don't understand. So let me try the other calculation that we had. We'll try number 3. Well, actually, let's just go through. So again, this one with the minus, this is what the original developer of GPUE thinks is correct. Here's the energy calculation I think would be correct if we were summing them. Let's do Julia Calc Energy. I think the minus isn't necessary because I think we implement the minus already. Your assumption about strings being folded in might be incorrect. Wait, what do you mean? Okay, calculate energy here. By the way, I really appreciate all the discussion here, guys. I have been trying to figure this out for a week, and I have no idea how to solve the issue. So I think I've adequately explained the problem. If you guys have questions, ideas, just throw them at me because I'm lost. If it were me, I'd go with the pen and paper until it all makes sense. I've got to go to bed now. All right, see you, Ben. Signs. Oh, signs, not strings. Okay. Yes, pencil and paper. No, but that is pencil and paper. So we've done the pencil and paper stuff already, right? So the pencil and paper stuff is what we did just a second ago. So page, new page before. So right, we're looking for page, new page before. So what we're looking to do is an integration over all space of negative infinity to positive infinity. Of basically the kinetic, potential, and energy, the kinetic term, the potential term, and then the angular momentum term. What we're using is the Fourier transform derivative. Let me check this out. So let's do Fourier transform derivative. Or something like this. There's a theorem that allows you to do derivatives based on Fourier transforms. We can also try just implementing like a straight up derivative. And if we implement a straight up derivative, maybe we could just implement the angular momentum step without needing the Fourier transforms. We could do that. So let's see, derivative. The derivative theorem says that, what are we looking for here? Given f to phi of f, so going from the time domain to the frequency domain, df of t of dt is going to be equal to I times 2 pi f of phi of f. So the idea here is that the derivative of the input function times dt is going to be equal to I times 2 pi f phi. Yeah, so that's just going to be the 2 pi kx term. So with every Fourier transform, you have these twiddle factors, which are e to the 2 pi ikx or whatever. So the idea here is basically we're taking the twiddle factors out. So we're performing basically a derivative in momentum space by multiplying it by these factors, the I to the 2 pi f. Again, we can try just doing a straight up derivative. We can try, instead of implementing these as a series of Fourier transforms, we implement them as just d by dx, you know? And so we could perform a derivative along x, along y, and along z. There has to be a way to do this in Julia, I'm sure, so we can try that. Check to see if that holds in Julia. Okay. So to be fair, we're getting basically the same thing with Python. So I don't think it's a Julia problem, but let's proceed into Julia. Let's run Julia. I was in the Python directory running Julia. It's kind of weird. Okay, so now we have Julia here. And what are we trying to do? We're trying to perform the derivative of a... so we're trying to perform a derivative here. So we're going to say A is going to be equal to 1, 2, 3, 4. So we know what the derivative here should be, right? Because it's going to be change, assuming that dx is 1, we should see 1, 1, 1, something weird. 1, 1, 1, something. I don't really know what's going to happen on the last step. So what we want to do then is we want to perform a Fourier transform and get the derivative here. So we're going to have to multiply it by something. So we're going to do FFT of A. So we're going to say B is going to be equal to FFT of A. Using FFTW. I've seen a Fourier transform function that's scaled by 2 pi I automatically, and so the scaling factor may not make some sense using that formula. Yeah, but there's something here that I'm missing here. Let me check something else. I don't like this particular... I'm sorry. I don't like this... I don't like this web page. I need to... Let me find another one that shows this more clearly or concisely. Let me get some water too. Okay. Oh, it is on. I was going to turn on the air conditioning because I'm hot, but it doesn't even matter. I could open up the blinds, I guess. It doesn't matter. Why would I open up the blinds? That would just make it hotter in here. Okay, let's see what we have here. Convolution, derivative seems fine. Fourier transform theorems, additional shift. This is literally, is this not the same one I was just on? Let's do differentiation. Okay. It's differentiation theorem. So it's saying that I want to go back to my skill pill that I taught on Fourier transforms when we were going through this, because I just remember it being so straightforward. You just multiply it by some factor in like momentum space and you get your derivative. Differentiation theorem. Yeah, let's take a look at this too. I don't know. I'm just so x prime is going to be equal to j times omega x here. So the idea then is let x of t denote a function differentiable for all t such that x, positive, negative, infinity equals 0, and the Fourier transforms of both x and t and x prime of t exist, where x prime of t denotes the time derivative of x of t. Then we have x prime of t. So let's see. So where it's going to be j omega x. So we multiply it by j omega x, where x omega denotes the Fourier transform of x of t. X, yeah, okay. In the operation notation, we're going to say Fourier transform underscore omega x prime is going to be equal to, so what we're going to try to do here is it's going to be the I of ft of some factor, but j here must be a complex element. So let's just see what happens. So we're going to do f of t here times some factor. I don't know. I have no idea. So we're going to say b. Well, let's just do I of ft of 2 times f of t of a. And I guess we're going to want to do im. So let's do 1 im. Ha! Yeah, that didn't do it. 1. 1, 2, 3. Obviously, that's the same thing. 2. 2, 4, 6, 8. You're just multiplying by the complex component. Well, let me see. Let's just go ahead and Google some performing derivative. Derivative on array Julia. See what we got here. Multidimensional differential gradient in Julia, approximate derivatives in Julia. Let's see what we got. Yep, that's what I'm looking for. Derive viz. I mean, we can just write our own derived function. It's not that big of a deal. We literally did it yesterday. I was just hoping for some library or something. So straight up extension of the definition of diff in Julia or 3D arrays. Let's see. My def. Yeah, let's just write our own function. I'm not too worried about this. I've seen a Fourier transform. Yeah, let's write our own derived function. I'm really not worried about this at all. Okay, so let's go into VI. Over here, we're just going to go into VI calc energy.jl. And let's just go ahead and create a function derive. Okay. So what we're going to want to do here is, I think we're just going to run similar notation to what we already have in GPUE. So let me just open up another terminal up here. Yep. Hello. Come on. There we go. Let's go into our implementation of the derive function in GPUE, and then we're going to kind of work from there. Again, if you guys have questions, comments, concerns, just let me know. As soon as I see it in chat, I'll do my best to answer it. So we're going to cd into projects, GPUE. Let's go into VI source, and I think it's going to be in kernels, and we're going to look for derive. Here it is down there. Okay. So what we're going to try to do is something like, we're going to want to read in the data. So let's see what we want the data. Thanks, man. So we're going to want data, the input data. So I guess this is going to be, I'm not going to define the type here. It doesn't really matter so much. So then we're going to want output data. But I think in this case, we can probably, no, we certainly want output data. Then we're going to want, oh, but we can actually just return the output data. So then we want stride, gsize, and dx, something like this. And we're just going to have to return out. And at the start here, we're going to say out is going to be equal to, we'll just say data, the input data. Okay, so now in here, we're just going to say, how are we going to do this? So we're going to say int gid. So I guess we're just going to go through the entire. So we want to perform a one-dimensional. Ah, dang it! I misspelled stride. Called it string. So we're going to want to perform a one-dimensional derivative here. So we'll say, I guess data is going to be a 2D object. So I guess let me just pop over here to Julia real quick, and we're just going to say A is going to be equal to 1, 2, 3, 4, 5, 6. Okay, and let's just say length of A1. A is 6. What I'm looking for, how do I find the length along a one-dimensional array? Or the length of one dimension of a two-dimensional array? Let's do length, oh my gosh. Length, Julia. Introducing Julia arrays. Range length equals 12, stop. Length. I guess I'll look for length with a parentheses. Let's see, length of A2. Do we know Fourier transform is in terms of S or omega? Because formulas are different. The Fourier transform, I mean, it's a discrete Fourier transform, right? So, what is S in this case? I don't understand why the formulas would be different. Length of permutations, length of X. No, but I want length of A. Oh, maybe I want size. Size of A1. Yeah, okay, that's right. So we want A of 2. Nice. So we're going to say, I guess we want the dimension that we're running across here. Yeah, so instead of stride, let's just go through. I guess we'll say dimension. Here. And so we're going to say for I equals 0, or 1 to size of a dim, right, and I guess we're just going to say out of, I don't know if this is going to work, but let's try it. So which dimension are we going to be going over? I guess we only have 2 dimensions to deal with here because we're only going to be doing a 2D summation. So I guess we're going to say if dim equals 1, else end, and here we're just going to say out. If it's along the first dimension, that should be out of I colon here. And then we're going to set this equal to, see, let's open up the GPUE one again. Should be equal to, 1 second. Oh, hello. I was on the wrong terminal. Ah, shoot. How did that happen? Ha! Screwed that one up big time. Big time. Okay, so we're going to pop over here, open up kernels.cu, go down to derive. And listen, here we have the derive function. So we're just going to say out is equal to data. Data. And then it's going to be of the element that we're on, so it's going to be I plus 1 minus data of I divided by dx. Okay, something like this. And then we're going to do the same thing down here, yank and paste down there. In this case, we're going to flip all these guys. So it should be R colon I, and then it should just be data of, in this case, it's going to be I plus 1 colon, and then I colon, and here it's going to be colon I. I know this is a dumb way to do it, but hey, you know, it is what it is. Okay, so now we should be performing a either a derivative along this dimension or along that dimension for a 2D array. Should be okay. Now the last thing we need to do is say if, and I guess we're looking for here, let's see, if we have a size there. So I guess we're going to say if, if I equals size of a dim here, then we're going to do some stuff here. So we're going to say if I is equal to that, then we're going to say if I is equal to size a dim. We're just dealing with the last element here. We'll say, why not? We'll wrap it around to the other side. This will be out. Paste. Oh, how did that? What? Else, if, oh, I see. And then we're just going to do an else here. And end there. Just mess around. Else, and end. Okay, now we're going to do I out here, and we're just going to say if we're on the last element, we're just going to say instead of I plus 1, we're just going to say this is going to be just 1. And the same thing is going to happen down here, just 1. Okay, cool. So we're just wrapping around to the other side. I'm not too worried about that. So now we have the function derive. We should be able to read this into the Julia guy. So if we do include calc energy .jl, it should just read it all in without any problems. And then we'll mess around with that derive function to make sure it works. Okay, so A is going to be equal to 1, 2, 3, and then we'll just pop down to the next line, 4, 5, 6. Then we'll do it again, 7, 8, 9. Okay, so now we have our 2D array, and I'm just going to perform derive along the first dimension. So it's going to be A along the first dimension. We don't even use G size, so I probably don't need G size. So let's go ahead and remove that. Whatever. G size doesn't matter. Let's do 10. I screwed that one up. And then dx is just going to be 1. 3, 3, 3, 3. Oh, okay, yep, that should be correct because that's along the columns. So if we do along the rows, 0, 0, 3. Oh, well that is not correct, is it? Okay, so if we perform a derivative along y, it seems to be okay because we are doing, we get 3, 3 and then like -4 or something like that. That's fine because we wrapped around to the other side. That was, I mean, that's a default or a problem with how I did it. However, this one is incorrect because it says, oh, unless A. Ah, I see the problem. I'm an idiot. Out is equal to this. Return out. Ah, what? Why did it set A equal out? A. Let's redefine A. Now we're going to say out equals this. Yeah, that's correct. And then out equals derive along the first dimension. Yeah, okay, that's correct. I don't know why it did that, but that's fine. So let's go ahead and remove g size from this derive function. Cool. So now we have a derive function that allows us to derive along the x dimension and the y dimension. So what I'm going to try to do is, without doing any Fourier transforms, I'm going to try to do this operation that we need to do, just with derivatives instead. So now we have a way to do a d by dx, and we have a way to do a d by dy. So in principle, we should be able to just do the energy L with a derivative along x, and work with that. So let's go ahead and comment this out. Let's see. I guess someone clipped that video. Wait, what video? What video are we talking about? Okay. Also, guys, I will be right back. Just give me a minute. Sorry about that. Okay, I'm back. Sorry about that. I see the problem. I'm an idiot. Oh, that's in general all problems that I have. They are solved by me realizing that I'm an idiot. So let's go back through here and let's see what we need to do. So again, we are relatively happy. Hey, Xion and Glyn? Xion? I'm sorry. Could you put a phonetic pronunciation of your name? Okay. Can you use C++? Yes, I can use C++. Okay. So what I'm going to do is I'm going to just kind of mess around with this a bit. So what we're looking for here is let's go back. We're looking for basically this operation. So it's going to be, let's do just the next page. It's going to be omega x py minus ypx, right? Psi. That's what we're looking for. I'll study language by you. Honestly, I might not be the best person to learn C++ from. My C++ code is basically C with a few additional features added in. Let me check something real quick here. Let's see. So my collaborator said they might have just found the problem. So looking at the script, I think calculating your EL, you're actually calculating LZ, which has units of H bar. So kilograms, meters squared, seconds squared. Need to multiply by this omega. Wait. Let me see. So they say maybe I figured out the problem. From looking at that script, I think calculating your EL, you're actually calculating LZ. She says this guy, the expectation value of LZ, which has units of H bar, so kilograms a meter squared, seconds minus 1. You need to multiply this by omega to get units of energy, i.e. kilograms, meter squared, seconds squared. If you calculate instead minus omega LZ, which drops your Hamiltonian in the rotating frame, this will have units of energy. Which is what I think makes sense compared to your other energies. Omega LZ. So what I need to tell her is that the omega, you are actually calculating H in the rotating frame. Does this make sense? I looked again and maybe you have omega hiding AX. Disregard that. Yep. So omega is in the AX and AY terms already. Let's see. To me, the first energy L looks almost correct. It's just missing the X and Y sign trouble. So in particular, and the negative Y is also already in the AY term. Let's see, conjugate psi. Let's see. Let's see. 1 second. I come from Taiwan. Hey, thanks for coming. 1 second, I got another message. Yep, sure. Sorry, this is my work time, so sometimes I get messages from people that I have to respond to. Let's see, so what they're saying then is, to me, the first energy L looks almost correct, but it looks like you're missing the X and Y and some sign trouble. It looks like you're calculating this conjugate of minus PY minus PX, where that should be calculated there is XPY minus YPX. So the reason I have this guy over here, let's just go ahead and respond to that here. So the reason I have this second energy calculation is because the negative sign should already be, that is why I think the second energy L should be correct, because it already has the negative omega and the negative y inbuilt to the AX and AY. But yes, but I'm still looking into it. I come from Taiwan. Oh, hey, glad to see you here. All right. Oh, thanks for the follow, man. Really appreciate it. Okay, 1 second. I just got a lot of notifications at the same time that I had to deal with. But that's okay. So we'll keep working on this. So now we have the derive function implemented. But let me try one more thing before continuing here. What I'm going to try is I'm going to take this guy. Oh, we just tried that too. Yeah, that also didn't work. Okay, never mind. We tried that too. I've also tried, I also want to mention, I tried all permutations of pluses and minuses. Okay, so we tried everything we could. So to me, the energy, let's see, where you should be calculating is conjugate psi dot xpy minus ypx psi for the calculation of LZ. Okay, so let's just go ahead and perform this derivative here. So I'm going to keep going, and we're just going to try to get this to work out. And I'm gonna come back to that in just a second. That comment that my collaborator had. I'm gonna come back to that and see if I can parse it. Okay, so here we have xpy minus ypx. Okay, so what we're gonna want to do then is px and py. So p is going to be equal to px is going to be equal to I h bar d over dx, right? So if it's xpy minus ypx, then what we're going to want to do is multiply by I h bar each of these times. So this is going to be y times I h bar derive psi. Yeah, okay, this is what we're looking for then. Okay, and then, yeah, so let's just give this guy a go. Let's see what happens. So we have the derive function now. So what we're going to say is we're going to say energy L is going to be equal to wave function conjugate dot times. And what we're looking for here is no FFTs anymore. This is just going to be a sum of these two variables put together. So what we're going to do is dot times, what am I looking for here? It should be I h bar. Do I have h bar? I'm just going to define h bar in here. What is h bar? Let me go to GPUE real quick. Oh, hello. I don't know what I just did there, but whatever. It doesn't matter. GPUE. There we are. We define it here, so I just want to take the same definition we have in GPUE. Join GitHub today. GitHub, what? I'm not signed in? How am I not signed in? Yep. Now I'm going to have to do two-factor authentication, aren't I? Oh, which means I'm going to have to blink the screen for a second. 6.6. Yeah, that's H, but H bar is going to be slightly different. Let me very quickly just change my screen real quick to say I'm doing something embarrassing, which I think should be that? No? Oh, I don't remember. Embarrassing screen up. Don't look. Let me go ahead and type in my password and stuff real quick. Okay, that should have to authenticate. Use, oh, wait, no, I know how to do this. Wait. I specifically, I remember. One second, I have to find my keys. Wait. Shotomate, sumimasen. Demo. Ho ho. Ho 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 ho. My dear friend. Oh, something went wrong. Just screw you. Something didn't go wrong. You can't see anything, but verify. Yeah, all right. Nice. Let me just It's h divided by 2 pi. No, you're right. You're right. I'm so glad no one saw that. That would have been embarrassing. Good thing I have this screen up. Okay, you're right. It is h bar divided by, I know it's h divided by 2 pi, but I think we're using different units. I just don't remember what units we're using. In Linux is usually what I use. I'm a Linux guy. What was I doing? I'm gonna do pi, observables, dot pi, control F, h bar, 1.05 times 10 to the negative 34. Yep. So we are using those units. I'm sorry. I know it's divided by. I know. So let's just say h bar is going to be equal to this. You were right. I'm sorry. TS just. Wait. You didn't see that, did you? Let me check real quick. Shoot. What am I doing with my life? 1 second. Open link. Oh, this is the Arch Linux one. Okay, so we have the h bar. So what we're going to do here, since I believe, let's go ahead and open up Zernal here. Since I believe we're going to have to multiply both by h bar, and both times I think I'm just going to multiply this whole thing by an h bar imaginary outside. So we're going to do h bar times IM, right? Not using atomic units is a sin. I'm sorry. I mean, you're right. So h bar times imaginary, and then we're going to multiply this by, and it will be ax times derive of wave function. Then we're going to want to be. Oh, this did something funny before, didn't it? Out data. No, this should work. So derive wave function along the second one, because again, second is x in this case. And then we're going to read in a dx, right? And then we're going to add in there a y, and we're adding in, I know it's xpy minus ypx, but the negative y is already inbuilt into the ax or ay term, so we should be okay. So it's going to be plus ay times derive, and I suppose in this case it should be a dot times, because it's element-wise. Oh, that should be a period. That should be a period. Let's try that again. And so it's derive wave function 1 dx dy. Okay, thanks. Oh, for the Linux thing? Yeah. And I think I have one more there. Okay, so let's see what happens if we run calculate energy now. What? Method error, objects of types complex bool are not callable. How did we get a complex bool out of that? What are we doing? Such that we failed miserably enough that we have a complex boolean. Oh, man. It says line 77. Calculate range. Oh, that doesn't help me. That's okay. Let's go to 72. Also doesn't help me. Okay, let's go to what line am I looking for here? Calculate energy. Complex. Yeah, right. What even is a complex boolean? Okay, energy L is wave function. I have a question for beginner. What language to study is better? For a beginner, I would argue that probably Python is the easiest language to learn. It's probably the most used. C and C++ give you, or C, I would say, gives you a good understanding of like what's happening with underlying memory management and stuff like that. But yeah, it does depend on what you want to do. TS Jost is right. Like if you're going to want to do game development, learn C#. or something like that for Unity engine. You know, it depends. Python is a good general purpose language that's easy enough to learn, I would say. H-bar imagine, what did I do to get a freaking derive wave function 2 dx dy ay dot times derive? I mean, obviously there's something wrong with the energy L function, right? Because if I just say this is equal to, and for web development, learn JavaScript. Oh, that's true. Yeah. I don't do much web development here. So how about I just remove this imaginary term here? You there. Remove this imaginary term here. Calculate energy. Yeah, you're still running into type of float 64 not callable. Okay. Energy L is equal wave function conjugate dot times. Just give me the line that you're having trouble with here, man. Calculate range line 72. Calculate energy line 39. Ah, you don't like this line. AX dot times derive of wave function 2. Okay. All languages are just different syntax. For the most part, yeah. You don't like this line. Why don't you like this line? Did it do something to you? Did it hurt you in some ways? I don't know. I have no idea. So let's just keep working on this. Why is this a problem? AX dot times derive wave function 2 dx. So I guess, I mean, I'm just going to define. Of course, it's not defined. Let's just go ahead and define the wave function as we've defined it in here then. So we're going to just scroll down a bit. Yep. So let's go ahead and just wave function equals read DLM here. Let's just paste it down here. Plus read DLM. Nice. Okay, let's try this. I think I need to put something there. There. Ah, fine. Wave function is equal to this. Oh my gosh, Julia. Plus this guy. Okay. That's not going to work because we need to define a data directory and I. So we're going to do data directory here. Now we're going to do I 0, so it should be fine. Okay, so now we're going to run that same command. We should get a wave function in. Nice. Now we're going to reshape it. There. Oh, I forgot. No? Oh, 256, 256. Okay. So we have it reshaped. Now let's go ahead and run this derive function, wave function 2. And we're just going to say a dx of 1. Works just fine. Okay. So say wave function 2 is equal to, oh my gosh, come on, wave function. Okay. So now we're going to say derive wave function. Here. Uh-huh. What are you doing, dog? Why are you doing that? Okay, so if we do a derivative of the wave function, it shouldn't be returning anything, but it seems to be returning something. So we're going to derive wave function. We're going to say wave function equals wave function 2. True. We're going to perform a derivative. Oh, okay, maybe it's not returning anything. Maybe I'm just being an idiot. Thanks, Turing complete list. Yeah. Okay, so we have derive wave function 2 dx. So we can do a dot multiplication by AX, but this, and I want to Google what ability I should have. If you're going to Google things, I mean, yeah, I mean, fair enough. You're going to have to Google basically everything, right? And that's totally fair. But you don't really have to learn too much before Googling things. You can probably find most things through Google. I just want to know what the error is that I'm looking at here. So let's just go ahead. Let's include it again. Let me get that error. Include calculate error.j, calculate energy. Oh, you want to work at Google? I don't know. I mean, they're doing a lot of machine learning stuff nowadays. So machine learning and AI, I mean, that's a general purpose useful tip. Just knowing a lot of AI is helpful. But I'm not really sure outside of that. Okay, method error, object type float 64 not callable. Derive wave function 2 dx. Derive wave function 1 dx. ay dot ax dot times h bar times. I have no idea. absolutely no idea what this error is trying to tell me. Calculate energy at line 39. Okay, so we're at line 39. 1 second, I got another notification. Okay. Then, wave function C, H bar, imaginary. What is this trying to tell me? Line 39, it says float 64 are not callable, but I'm not calling a float 64 so far as I'm aware. AX dot times FFT derive. Well, let's just see where it breaks. So we're just going to do this. Comment that out. Doesn't like that either. What's your problem then? H bar is equal to this. Is it the H bar it doesn't like? Oh, never mind. I know what the problem is. No, I don't know what the problem is. Machine learning plus programming language equals Google worker? Not necessarily, but I mean, you need to be kind of top of your class, like best of the best to be Google, I think, for the most part. But yeah, machine learning is a good way to get your foot in the door. Is not a unary operator. I mean... Aha. I did the same mistake I did before. So let's try H bar times IM times this. Let's go. Okay. Okay. Yeah. This is what I expect. So let's try it without the energy L. Okay, now let's see what the energy L is in terms of order of magnitude. 743, because it looks like it's not affecting our system at all. And I was expecting it to be the dominant component. Yep, comma typo. Thanks, okay, Raider. But now it looks like energy L isn't affecting our system at all. So what I'm going to do is I'm just going to yank paste. I'm going to comment this guy out. I'm just going to say this is energy L. All right, so now we're just looking at energy L. And we're just going to DT here. Let's do include. That is identically 0. Shoot. Okay, so that means we're wrong. I don't exactly know how, but we are wrong. Well, here now we have a whole bunch of energies. And they're way too high. Look at that. 2.76 times 10 to the negative 21st. So now we multiply this by H bar. Oh, I know why. Include this. So then now these guys are still times 10 to the negative 12th, which is way too high. Dang. Dang. Okay. Let me think here. So we know that the momentum operator is IH bar, d by dx, or d by dy. Is there a 2m we're missing here? No, because the 2m is in the Hamiltonian. I'm at a loss. Yeah, I'm at a complete loss. It's negative IH bar d psi by dx, right? So we have d by dx. So we have our d by dx term. We have p is negative IH bar d by dx, right? Fine. This is we made sure the derivative we were performing was correct. Then we have a negative IH bar. Put the negative in there, but I don't think this is really going to help any. So let's do negative 1 times IM times H bar. And we're just going to do include, calculate energy. Yeah, and of course they're all going to be 0 because we're multiplying by that imaginary component there. Let me try taking out that imaginary component. see what order of magnitude we're at. We're still too high. No matter what, we're too high. Times IM. Yeah, I'm still, don't know why, but I'm getting the feeling there's either 2 pi missing or one where there shouldn't be. Yeah, but 2 pi doesn't give us 10 to the 13, you know? Like 2 pi gives us 10 to the 1. We're off by a huge order of magnitude here. I just can't figure it out. Let me check to see what we have here. No, I was hoping for another comment. But I didn't get any more comments. Come on. So -1 IM h bar ax dot times derive wave function 2 dx, wave function 1 dy. Okay. So, I don't know. I have no idea. Let me go ahead and get some water. So we did a derivative by dx, we did a derivative by dy. We multiply by the ay component, we multiply by the ax component, we put in an h bar, we put in negative I h bar. But wait a minute, that I h bar, so what's happening is that negative I h bar, how about let me not return the real. Let's just return the imaginary too. Why not? So here we have the energy here. Let's just return energy L. We're going to do include calculate energy.jl. Now, we're still 10 to the minus 12, and we should be 10 to the minus 33. So we are 20 orders of magnitude too high. Yeah, we're way too high. Shoot. Yeah, I have no idea. I'm just completely lost. Well, let me go through and let me reread what this person is saying over here. I think maybe, yeah, I'm not sure. So AY, for example, is negative omega and AX negative omega PX. You still need X and Y parts. There should be a difference in sign, I think. Yes, so a y is going to be equal to omega py, because AX is equal to negative omega px. Okay, well, I think I might go ahead. Why does it go from 55 to 12? Yeah, I don't know. I have no idea. I have absolutely no idea whatsoever. Let's see. So they're saying, so for example, when I'm calculating LZ in MATLAB, I do something like x dx1 is xm IFFT. Gosh, that's impossible to parse. Holy cow. MATLAB code, man. Every time. XM. What the heck is XM? PZM? Yeah, I don't know what any of that means at all. Yeah, okay, well, so what they're saying is you do xdz1 is equal to xm IFFT PZM any bathrobe donners in chat today. I don't know what that means. I don't think there are, but I think maybe we'll just call it for now. I tried everything I could again. I'm just gonna kind of keep messing around with this and see what we got, and I'll just keep working on that. X matrix, PZ matrix. Yeah, but we don't have a PZ in this case because it's only 2D. Anyway, I'll keep working on this. I'll see what we can get. I think that's it for the day. Let's go ahead and see who we can raid. I don't know if anyone's online. Loading artist. Yeah, I don't see anyone online that I would normally raid. So if you guys have an idea, let me know. Other than that, I think we'll go ahead and close it for now. let me know if you guys want me to do more of these research streams or not. I mean, it's 50-50 for me, you know, like, I think they're a good idea to do because I think I should be more clear and open about what we're doing. But on the same time, we run into situations like this where I'm just completely baffled and have no idea what I'm doing. So I kind of want to be more open about the research that I do, but I'm not sure the best way to do that. So, I mean, Fulster says yes. I can try to do more when I can. I mean, I can't guarantee like a set schedule or anything, but I can try to do more every now and again. Okay, so I think that's it for now. I'm going to keep working on this through lunch. It's 11 o'clock my time, 11 o'clock a.m. my time, and I need to be in the office. I need to be in the office by 1 o'clock this afternoon. So I was going to keep working on this for the next hour, just on my own time, see if I can figure it out. And if I can't, I'm just going to go into work and work on it there. So anyway, guys, thanks again for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you around next time for the next episode of Simuleos, which will be tomorrow morning. I think, although I'm not sure, I think we might do an Article 13 discussion. Like, I just want to learn about Article 13 and see what it is. Like, I just want to learn about this whole, like, copyright stuff that's going on in the EU. I'm very interested in it, and I just don't know about it. And I know it's a big deal, but I don't know exactly how big of a deal it is. So I just kind of want to look into this. So we might do that tomorrow, or we might go back to domain coloring. I'm not really sure. On Saturday, we'll come back in the morning, again, 5 to 7 a.m. my time, and we'll do some discussion about, you know, I'll actually do the setup for my tablet and stuff. That's it, guys. Thanks so much for coming in. And yeah, I guess I'm not going to host anybody because I didn't really see anyone online that I normally host. So I'm just going to head out. Have a wonderful day, guys. See you next time. Bye.